Howdy, today on Flippin Science we're going to look at disease control. So the science understanding we're going to look at, we're looking at examples of disease control, including controlling carriers, killing pathogens, quarantine, and the immune response. So disease outbreaks can have big consequences for the areas where the outbreak has occurred, the countries that are managing the disease, but also globally. We can have epidemics turning into pandemics when they spread from country to continent and then around the world. So stopping the disease can have many benefits for society. You have workers that can work rather than being sick. They can be earning money, which helps the economy. And you allow the free movement of things, which is good for the environment. But there can be ethical costs for controlling diseases. So there's benefits and also problems with some of these things too when you're controlling a disease. So let's look at some of those things now. So a vector is something that carries a disease. Normally we think of vectors in terms of living vectors, which are things like mosquitoes, ticks and fleas that are animals that spread disease. They are carrying the disease-causing pathogen. They themselves might not be affected by the pathogen, but they carry it and they can pass it on. But a vector can also be something like dust, which carries disease too. The idea is that if you can control the vector, then you can reduce the spread of the disease. And this can be done in a variety of ways, particularly if they're animals. Mosquitoes are known for spreading malaria, as well as yellow fever and a few other diseases. And they reproduce using standing water. So standing water is still water that isn't moving too much. Their young grow up in standing water before they turn into the adult mosquitoes. So if you can control the amount of standing water around, you can reduce the number of mosquitoes. One way of doing that is by spreading poison. Down here we have a picture of some kids. There's a truck over here that's driving along and it's spraying this gas. This gas here is DDT, which was an insecticide used for quite a while. So by doing this spraying, you're killing the mosquitoes. You can spray insecticides directly into standing water, or you can just spray in a wide way like this is. If you're killing the mosquitoes, then you're stopping the spread of the disease. Now, this can be costly. It costs money to do something like this, and also to have people patrolling and looking for standing water. And also there can be environmental impacts of spraying a pesticide like DDT. DDT builds up in fatty tissue in organisms, and it builds up in food chains. So organisms at the top can get really, really high levels of DDT because they're eating things that eat lots of things that contain DDT. There's also environmental impacts of getting rid of mosquitoes, because mosquitoes can be pollinators for some flowers and plants. So if you get rid of the mosquitoes, then you can damage those plants too. Whenever you affect anything in the ecosystem, there are other effects further up in or around in the ecosystem too. So that's something to be considerate of. You can also kill the pathogens directly, and this can be done with antibiotics, antiseptics, antibacterials. Antiseptics are present in many cleaning products, and there's a wide variety of antiseptic chemicals that can kill pathogens like bacteria. They can kill other things as well, so your protists, viruses can be destroyed by some antiseptics. So by killing that off, you're reducing the spread of it. Antibiotics have been around for 60 or 70 years by now, and they kill bacteria in a variety of ways depending on the antibiotic that you're using. In this picture here we can see we've got a plate with a lawn of bacteria on it, and we can see each of these discs has been soaked in a particular antibiotic. So we can see some that are very effective. So this one here, I can't read what that is off of it. This one here is penicillin. Down here we have ampicillin. Both of these aren't effective at all. We can see the bacteria still growing around them, but these ones here, these seem to be killing off this particular species of bacteria. Now there's problems with using antiseptics and antibiotics, depending on which ones they are. Alcohol is often used to kill off bacteria, for example. It's in hand sanitizer, lotion. It's very unlikely that bacteria will be able to evolve around alcohol. Alcohol in high concentrations is very toxic. But some antiseptics and antibiotics are being evolved around by bacteria. An example is triclosan. So triclosan is in a lot of soaps that claim to be antibacterial. The problem is by using lots of triclosan, it's building up in the environment, and that means that bacteria can evolve what we call resistance. And the way this works is you expose the bacteria to the antibacterial or antibiotic, which kills off most of the bacteria, but the bacteria that aren't killed off by the antibiotic or antibacterial they are immune to it, so they can reproduce, and then they have immunity completely from that antibacterial or antibiotic. What's interesting about bacteria, they can also pass the genes for antibiotic resistance to other bacteria, so individual bacteria, but also completely different species of bacteria. And that's what this little animation down here is showing. As we go along from one side to the other, we're increasing the concentration of an antibiotic by 10 times. Now this is a time lapse of over 10 days. So the bacteria colonize one area, and then they get to an area where there's 10 times more antibiotic in the environment. And you see little sprigs where a particular bacterium has evolved around that antibiotic. Then they get to another barrier where there's another 10 times increase, and we get new bacteria evolving new ways to get around the antibiotic, and so on and so on. So it took 10 days in total to cover this screen, which is several meters long. The problem with evolving resistance is then we can't treat the bacteria that are causing infections. This can occur in hospitals where there's antibiotics commonly present in the environment, and it happens with something called MRSA, which is methicillin-resistant Staphylococcus aureus. So Staphylococcus aureus is called golden staph. It's present on your skin normally, and it can cause infections in particular situations. And when it causes an infection, it's treated with an antibiotic. As the antibiotics stop working, you use different antibiotics, and then there's this one antibiotic called methicillin, which is the last line of resistance antibiotic. It's the one you use last. So MRSA bacteria are resistant to methicillin, so they can't be treated. They can't be killed off by the antibiotic. So the infection can spread. It can spread in people inside the person, but it can also spread to other people in the hospital, for example, or into the community. It's costly to develop new antibiotics, so not much research is carried out by pharmaceutical companies because they don't make a lot of money off of antibiotics. They make a lot more money off of drugs that you have to take regularly for your entire life, rather than antibiotics which you might take for 1 or 2 weeks. There's an ethical issue with prescribing antibiotics to people who are infected with bacterial diseases. Obviously you do if you're reducing pain and suffering, but if you overprescribe, then you can lead to resistance, which would cause more harm in the future. Quarantine is another way to reduce the spread of disease. What quarantine is you're enforcing people to be isolated so that they don't infect other people. This prevents the spread of disease by stopping people from being able to contact other people and therefore pass on the pathogen. If it's airborne, you keep them in areas where they can't breathe on other people, or you might put them in little tents and have everyone around them using suits. If it's by direct contact or skin contact, again, you isolate them so that they can't touch other people while they're infectious. This can be quite costly, so setting up a unit like this in a hospital can cost a lot of money, and you need to have specialist staff that are trained in the use of and how to deal with quarantine and how to use the equipment in particular, so it can be quite costly. There's also ethical issues. So in the past there's been quarantine boats. There's a special flag that indicates quarantine. The word comes from the Latin word for 40, which is how long a ship had to be at sea outside of a port if it was carried people infected with the plague. So 40 days it had to be out there. Quarantine ships were used for a very long time. There's also ethical issues associated with quarantine. So over here we have a picture from, well, not from the Black Death, but showing what happened in the Black Death. If a person was infected with plague, then what could happen was that the door to their house was locked up, a red cross was put on the front of it, and that said to people not to come into the house, and the people could be locked up inside the house, even if there's one infected person and the rest of the people in the house weren't infected. And then that would mean that the person who was infected is passing on the plague to the people who weren't infected, so everyone in the house essentially dies. So there's ethical issues there. How long do you keep people in quarantine? Should people with particular disorders be quarantined if they're not particularly infectious? So there's lots of things to be considered if you're going to quarantine someone. If a person is infected with the pathogen, their immune system will spring into action and produce, depending on what the infection is, a variety of different ways of dealing with that. If you treat people who are infected and you treat how their immune system is responding, you can reduce the impact of the disorder on the person. One thing when someone gets sick, normally you'll send them home and you'll say, hop in bed and sleep. That way they're isolating themselves from their people at their workplace or their school, and they're less likely to infect other people. If someone's having an immune response and you treat that, that can reduce the impact on them. So if someone's got a fever, for example, you treat the fever. The fever's there to try and kill off the pathogen, so it's an immune response that makes sense, but the person can feel quite bad, and if the fever gets too high, that can be very bad for their health too. One way of using the immune response to stop the spread of disease is to have vaccinations and immunizations if they're available. Vaccines aren't available for all pathogens. Depending on the pathogen, there might be a vaccine or not. Some common vaccines will work for a short period of time, but they don't work long term because the pathogen mutates itself, so it can change itself. So you have to get a new flu vaccination every year because the flu virus changes from year to year due to this mutation. If there's no vaccine available, then you can't really use this as a way to stop the spread of the disease. So today on Flipping Science, we looked at a variety of ways of stopping the spread of infectious disease and their impacts. That's it for Flipping Science today. See ya.